Okay, so welcome to lecture 9, which is actually the final lecture in statistics, the one of our two lectures in statistics. Uh, and what we're going to be looking at today is how we can look at something called bivariate data. In last week's lecture, we looked at when we had data which is progressing in time, and we can group this data, and we created histograms. We started looking at central tendencies, and it began to give us an idea of what happens if we have a very large set of data, how we can manipulate it, and how we can shrink it, and how we can make it visually impactful, and how we can actually begin to understand these data. And one thing I'll point out here is often when I mark some of the work from second year or maybe even third year work, it's very apparent that some people don't understand how to use these tools. So even just appreciating the usefulness of these statistical tools, and maybe some we're going to look at today, is really important. Often the mean value, the standard deviation, the median, the mode, and the range are going to show us a lot more information than something such as the p-test or p-value or the t-test. We can actually physically see something with maybe a whisker plot. We can see how data spread with a histogram. We can find out how there's modes in data. And today we're actually going to look at what happens if we have two types of data varying at once. So maybe we call this bivariate data. So the example I've given in the book is if we had some waves, or we think of the ocean maybe, and we think of the height of some waves, and we think of their power and how they vary. So what we could do is if we have a set of data, maybe we create two axes. It doesn't really matter which way these axes are. And I'll put this as height and this as power. And what we could do is if we began to plot these data, and something like this, something like what we see on the data plot, we might get something that looks like this. And often we try and go into Excel and fit a straight line through this. So this isn't the best example, but as I show further on, maybe if we have a lot of data, maybe thousands of data points, maybe even millions of data points, what we can do is we can begin to create correlations. So maybe we have some data that looks a little bit like this. So varying wave height and wave power, quite realistically, as the height of the wave increases, the power would decrease. And this is what we call a positive correlation. Likewise, maybe we have something that looks a little bit like this, where we have maybe the wave height versus the wave frequency. And we probably see the data begin to tend a little bit like this. And what it would show us is that wave height has a negative correlation with the frequency. So just plotting the data on a correlation, I've spelled it right there, just plotting the data on a scatter plot, putting it straight into Excel, gives us an idea of what's actually happening with the data set. It can give us a feel for the data. We don't talk about it in this module, but often we have something called outliers in data. Don't worry too much about those, but that's part of experiments, and it's also there's a lot of research which goes into understanding what outliers are. Okay, so I've just talked about these straight lines, and it's great. So maybe we'll start here, and we have a set of data. It could be A and B, doesn't really matter what it is. And we plot them, and we might see something that looks a little bit like this. So at high school, you were shown to get your ruler out, and we kind of fitted a straight line like this. So this straight line was a bit of a guess, so we might have another point there, and this guess helps us to describe the work. But it's not very scientific. And you might know, you might not know, that actually Excel does this as well for you. It's called a trend line. And Excel is basically fitting this straight line to describe all of these data. And a little bit like last week when we're describing that we have central tendency in the mean, which describes the data when we have one variable. Well, when we have these two variables, what we can use is we can use a straight line to help us describe how these two relationships are between this A and B category are. So what are we actually doing? So how does Excel do this, and how can we actually get something mathematically which is going to help us describe this? We could start with a straight line, then we can move to curves, we could move to sinusoids, we could move to descriptions, and we could move to models. And again, you might be thinking, why is this really important to me? I'm a geographer, or I'm an environmental scientist, or an oceanographer. Well, actually, especially in all of those topics, oceanography, geography, geodata science, geology, we're becoming very data heavy. And what we need to do is have the statistical tools and the statistical understanding to be able to deal with this data and actually create these relationships. So anyway, I digress. If we have a line here that we're going to fit, we will fit that to our y equals mx plus c. So what we're trying to do with this line and what we've done with our ruler is we've found the distances between all of these points a little bit like this. And we've tried to find the minimum distance out of all of these, or the sum of the distances. We've tried to find the minimum distance which this line fits quite nicely to. As you can see from here, it's not probably drawn correctly, it's not drawn great, but we can see that this fits in between the lines. Okay, so what does this mean? So how can we actually get to an equation or a physical way of doing this? So let's just start by maybe taking one of these points, and we're going to draw a set of axes again. We'll put our y-axis here, our x-axis here, and we're going to put a straight line. So I've told you this fits y equals mx plus c, but we're just going to change this round a little bit. For this case of this example, we're going to put y equals a plus bx. Okay, it doesn't really matter. It's exactly the same thing. So we're now going to choose one of these points a little bit here. That's just a random point, and we're trying to fit this line to a number of points. So what we say is if we call this point P, that would be Px and y. But as I showed you last week, we have something where we have this little subscript here, which shows that we have a vector, which is actually tensor notation, this, and it shows us that we have multiple of these points. So we can think of these as a number of points. So, okay, so we can say, well, if we know what P is, that would fit quite nicely on a line. We might call this point Q. Likewise, we won't put in this point P, and we might call this point Q, where it bisects this line that we're trying to fit it. Likewise, we're going to have a point xi, which we describe here, which are going to be multiple points along the x-axis, and we could call this k. So we know to fit this onto this straight line, well, we can actually describe this straight line, which would be our y equals a plus bx, but we know what x is, so we could say that this is a plus b subscript I. So this helps us kind of describe the beginnings of the line. Okay, so now we have this. What we're trying to do is we have multiple of these p-values, and we're trying to fit them onto the line. So we need to find a way in which we can find the distance from P to Q. So what we can say there with all of this information is that our P to Q equals y I minus our A here, and then we minus our BXI as well, because we're minusing it from here, we're going from here to here, and we now have a description which is going to show us from P to Q. As with the standard deviation last week, I told you we squared it because this helps us get around the problem if we have a negative or a positive value. So we have here. So this now is a description, and it's actually a description of our slope, S. So this is showing our change about two variables, A and B. So we could say that our S is equal to yi minus A minus BXI all squared. Okay, so what did we do a couple of weeks ago? What we want to do is minimize this A and this B. And the way we minimize things, as we showed last week or the week before, not last week, about 4 weeks ago in the differentiation lecture, is we do this by differentiation. So we want to solve for A and for B, or in terms of A and B. So what we can simply say is that the ds by dA would equal 0, and ds by dB is also equal to 0. Okay, so now we've got this equation, and this is basically minimizing it. So you might even see something in mathematics where you might have this same problem, A and B and min. This is how we typically write this. So if this is often how I would put it to solve a problem. And what we're basically saying is here, if we had these values, maybe this is a capital A and a capital B to keep to our subscript, our A and our B, where have we gone? Here, by minimizing A and B with a minimize, what we're doing is we're creating this descriptor of this line. We're finding the gradient, and that's all we're trying to do with this slope here. So if we want to find the minimum A and the minimum B to make sure that this fits on well, we just have to differentiate. So as we found out the last couple of weeks, if we differentiate ds with respect to A of this value, we would get, we have a 2 here, we have a negative A, so that'd be negative 2, yi minus A minus bxi, and that all equals 0. And if we want to do that with respect to B, that would be also equal to, well, we have a 2 here, so that would be a negative 2. We'd have a brackets open. We also have the x on the B, so that would be another xi. Then we have a yi minus A minus bxi. So if you haven't followed that, do go back to the calculus lectures, and we're just following that rule that we saw a few weeks ago where we have the squared power. So where we get the negative, and this is where we get the 2. Okay, so we've now worked out something with a slope with respect to A and respect to B. So let's see if we can just neaten up these equations. So what we're trying to do is actually make this in terms of something that we're physically describing. So what we can say is, well, we'd need to sum all these up. So this would mean that our ds by dA, we could now write as minus 2, I equals 1 to our n values, yi minus A minus bxi, or with brackets. Okay, and likewise, we could tidy this up, was to say that our ds over dB would equal to minus 2, our sigma again, I equals 1, n, open our brackets, open our brackets. We have our x, right? Our x inside of the brackets, because we have to keep this summation inside of this summation, this subscript inside of the summation, yi minus A minus bxi. And again, those equal to 0. So we can still tidy this up a little bit more and maybe put it into a form that we're more familiar with. So maybe we want to put this into terms of y. So we could neaten this up to just say that this, well, is equal to, oh, so maybe not equal to, but this then is our sigma n I equals 1 minus, of our yi, so we split it up, minus, well, if we have no subscript, this would just be multiplied by n, so na minus b sigma n, can't draw sigmas, sigma n, I equals 1, xi equals 0. Okay, so we're nearly getting this into a y equals mx plus c format. We can see we have the a, we have the b, we have a y, but we don't actually have we have the x. So we could then perhaps neaten that up to put it in terms of y. So we could say sigma yi, I equals 1, n equals an plus b sigma I equals 1, n xi. Okay, so now we have quite a neat form here. So likewise, we can do the same to the second equation. So we could say our equation here, if we were to neaten it up, we put our sigmas in, so that's down to here, there's a b. We can say that that is then equal to our sigma, ni equals 1, xi, yi, minus a, sigma n xi, I equals 1, minus b, sigma n, I equals 1, x squared I, that all equals 0, and we can then multiply this out to get it in terms of y. We actually have an x here, so it'd still be in terms of y. So we have our summation, and I equals 1 equals a sigma n I equals 1 xi plus b sigma n I equals 1 x squared I. Okay, so we now have these two equations, and this looks kind of complicated, but we're now going to go and simplify it. So we have this equation here and this equation here, and these are both in terms of y. So if we just get rid of a few of these subscripts and just neaten this up a bit, what we can actually find is we now have a set of simultaneous equations where we have something like an plus b sigma x equals y. So we've missed the limits on the top. Don't worry about that. We're just doing it to tidy it up. And a sigma x plus b sigma x squared equals sigma xy. So with these simultaneous equations, we can now find our A, our B, our A and our B values, which will put us back into this form of y equals A plus bx. So this will help us get to y equals A plus bx. Okay, so that looks quite simple. That looks quite difficult, but let's do an example and show how simple this is. Okay, so if we take an example of data here, I've written it as x and y, and we have minus 2.4, minus 0.8, 0.3, 1.9, 3.2, minus 5.0, minus 1.5, 2.5, 6.4, and 11.0. Okay, so that's our data. So what we've seen from these equations is we just need to do some kind of adding up. We want to find something in returns of x and y, x squared, and x and y. So this means we can just create a table. So we say that if we have our x, we have our y, we want an xy, and we actually want an x squared as well. So we put this in here, and we just begin to fill out the table. So we would say our x would be minus 2.4, minus 0.8, minus, it'd be 0.3, 1.9, 3.2. And then likewise, we have our y, which is minus 5, minus 1.5, 2.5, 6.4, and 11.0. We have our xy, which we stick these into a calculator, which is just these two times each other, which is 5.76, 0.64, 0.09, 3.61, and 10.24. And our x squared, which is 12.0, 1.2, 0.75, 12.16 and 35.20. Okay, so great. So what we've said in this equation is we actually want the sum of these. So this is our sigma value here. So all we do is we add all these up, and this will give us the answer is 2.2, 13.4, 20.34, and 61.31. So then all we have to do is fill out our equations, which we have here. We want to find out our x, our y. We know this, we know this, we know this, we know this, and now we know this. So if we just sub all this in, we can actually find that the answer would be, so A, there's n numbers. So if we write out A, n plus B sigma x equals sigma y, and A sigma x plus B sigma x squared equals sigma xy. We know there's n numbers. There's 1, 2, 3, 4, 5 numbers here. So that is 5 pencil word, A plus 5A plus our sigma x is 2.2, 2.2b equals sigma y. So sigma y is our next one, which is 13.4. And then we do the same for the one underneath. We would say that would be A sigma x, which would be 2.2 plus B sigma x squared. So that'd be B sigma x squared. So that's poor writing. So it'd be 2.2a plus B sigma x squared, which is 20.34b, is equal to 61.31, which comes from here, our sigma xy. And what we have here is we have a set of simultaneous equations. These are quite simple simultaneous equations. All we need to do now is solve for A, and if we can add these together to get there, or we can do by substitution, which means that we would get that our A value equals 1.421 and our B value equals 2.861. You can follow this through and check it. It is in the handbook. I'm not going through it for the sake of this lecture. So now we can say if we want to put this back into the original form which we started, which was here, y equals a plus bx. So that'll be y equals 1.421 plus 2.861x. And that is in the form, or maybe we want to write it in y equals mx plus c, so y equals 2.861x plus 1.421, and that is in the form of y equals mx plus c. So what we've done is for all of these data here, we've fitted a straight line. And if you wanted to check that in Excel, which I have done actually in the book, you'll find that that is the correct answer. So not that bad for a straight line. It now looks like you'll never ever need to use your ruler again. So we'll come back to this in the final part of the lecture. So that was how to use least mean square to fit a rule. We're now going to look at growth and decays and how we can look at exponential curves.